In order to make measurements, we need to have a standard that we agree upon in order for our measurements to be the same for replicate measurements. And so in science, this is really important, and we need to make sure that we include those units when we are making our measurements. So why are units so important? Well, NASA found out how important it was to label and make sure you communicate which units you're using when they lost a $125 million Mars climate orbiter. Because they were using two different units on their calculations, it ended up burning up in the Martian atmosphere instead of monitoring the weather that it was designed for. So this is an extreme example, but it is essential that you include units and make sure you communicate those units to people you're working with. The standard units that we use in sciences are the metric system, and it's agreed upon set of international units that is abbreviated SI units because of the French translation. And these units are, if we're measuring length, it is the meter, and its symbol is M, and this is based on, or it's measured by the distance that light travels in a very specific amount of time. Mass is measured as a kilogram, and kilo is the prefix that tells us that it's 1,000 times larger than a gram. The mass, or the kilogram, used to be a cylinder made out of platinum and iridium and stored in Paris, but they were starting to notice differences between their identical cylinders, and so they have just recently moved to using the watt balance in order to define a kilogram. Time, its unit is seconds, which we're all quite familiar with, and temperature is measured in Kelvin. So for temperature, we're pretty familiar with the Fahrenheit scale. This is what we use in the United States. Everywhere else in the world uses Celsius. And the Celsius scale is based on where water freezes and where it boils, and evenly splitting those differences into 100 even spaces. In science, we use the Kelvin scale. This is an absolute scale, which means it's based on where all motion ceases in molecules. We're setting that as the 0 point, also known as absolute zero. The size of the degree is exactly the same as Celsius. There are no negative numbers in the Kelvin scale. You may also notice that there is no degree sign on Kelvin. So for Celsius, there's a degree Celsius, a degree Fahrenheit, but for Kelvin, it is just Kelvin. Now, in order to calculate between these scales, the equation uses the difference in our 0 point. So for our degrees Celsius, the difference between Fahrenheit and Celsius is 32. And so that's why we're subtracting 32 here. This 1.8, the reason we're dividing by 1.8 is that is the difference in the size of the degree. So Fahrenheit is a different increment. There's not 100 even spaces between 32 and 212. For the Kelvin, in order to calculate Kelvin, it's the degrees Celsius plus 273.15, and this again comes from the difference in the 0 point. So 0 degrees Celsius is 273 Kelvin. There's no division in this case because the degree sizes are identical. This is a very important equation to know. Kelvin equals degrees Celsius plus 273.15. If you need degrees Celsius to Fahrenheit, you're welcome to look that value up. But we do use degrees Celsius to Kelvin quite frequently in this class. So this little cartoon is just to put things into perspective for you. Compares 0 and 100 for each of the scales. So if it's 0 Fahrenheit, that is really cold outside, so well below freezing. If it's 100 Fahrenheit, that's really hot outside, like a very warm summer's day. When we go to Celsius, if it's 0 degrees out, it's fairly cold. It's where water freezes, where it could potentially start snowing. If it's 100 degrees Celsius, you're dead, because that is 212 Fahrenheit, and we can't survive in those conditions. If we look at the Kelvin scale, at 0 Kelvin, you're dead. At 100 Kelvin, you're dead. And that's because both of those temperatures are very, very cold, and we would not be able to survive them. Let's look at doing a calculation. So in this course, I'm going to give you example calculations where I walk you through them. And then I'm going to give you a practice where I ask you, if we were face-to-face, I'd give you time to work the problems in class. But because we're watching a video and you're provided a video, I'm going to ask you to pause the video, try the problem on your own before you watch the solution. That way you can identify any places where you have questions or what you don't quite understand about the problem. So the book lays out ways to solve problems, and the first thing that it asks you to do is to figure out what you're given in the problem. So in this case, we're going to start by taking 40 degrees Celsius and converting it to Kelvin. So we are given 40 degrees Celsius. We're trying to find Kelvin, and our equation for that is Kelvin equals degrees Celsius plus 273.15. So now, based on our equation, we can plug in our numbers to solve the problem. So Kelvin is equal to 40 degrees Celsius plus our 273.15. We do that calculation, come out to 313.15 Kelvin. Okay. Now, if we want to find 40 degrees Celsius in Fahrenheit, again, we're given our 40 degrees Celsius. We're trying to find degrees Fahrenheit, and our equation, degrees Celsius is equal to our degrees Fahrenheit minus 32 divided by 1.8. Now, because our equation, we're trying to solve for Fahrenheit, we need to rearrange it. So to rearrange it, we have to bring the 1.8 out of the denominator. So we have 1.8 times our degrees Celsius. We have to move the negative 32 over to the other side, and so we have to add that to get rid of the negative 32, and that equals our degrees Fahrenheit. Now we can plug in our degrees Celsius to calculate our answer. And what we end up with is 104 degrees Fahrenheit. Now, a very important part about doing problems is to check to make sure that they make sense. So our number got bigger for Kelvin, which makes sense because we're adding our 273. For Fahrenheit, okay, 40 degrees Celsius, they also got bigger for Fahrenheit, which makes sense. Just as a reference for you, degrees Celsius, room temperature in degrees Celsius is about 23 degrees Celsius, and Fahrenheit and Celsius are equal at -40 degrees. So -40 Fahrenheit is -40 Celsius, just to give you some reference points. All right, so here is a problem to practice. Convert degrees Fahrenheit into Kelvin. You'll want to pause the video and try this problem. So what are we given? We're given 0 degrees Fahrenheit. We're trying to find Kelvin. So in order to do that, we want to start with our degrees Fahrenheit, convert to degrees Celsius, and then finally to Kelvin. So we're going to need a couple equations to do this. We're going to need our degrees Celsius equation. And we're going to need our Kelvin equation. Degrees Celsius plus 273.15. Okay, so the very first thing we're going to do is we're going to substitute in our Fahrenheit. Minus 32 divided by 1.8, and we end up with degrees Celsius equals -17.8 degrees Celsius. Now that we have that value, we can plug it into the equation for Kelvin. Adding our 273.15. So Kelvin would be 255.37, sorry, 0.35 Kelvin. So the next thing is to do significant figures and round. We'll talk about this in the next section, but we would round this to 255 Kelvin, and we'll explain why that is in the next section. Again, we want to check our answer. So because 0 degrees Fahrenheit is less than 0 degrees Celsius, we would expect to have a smaller value than 273, which we do. So that would make sense. We're going to use prefix multipliers with our SI system. So our prefix multipliers that we're going to use most frequently are the ones with the pink stars next to them. And these are the ones that you're going to want to be able to convert into or convert out of into other values. So what this means is that whatever our base unit is, whatever measurement we're making, so if we were making meters, we would take and have, for a megameter, that would be 1,000 meters. And we would abbreviate it capital M, lowercase m. So a megameter would be 10 to the 6th meters, or 1 million meters. If we had a kilometer or a kilometer, then it's 1,000 meters. Our base unit would fall in the middle here, so that would just be 1. So if you're talking meters, it would be 1 meter. And then we get smaller. So a centimeter is 1/100th of a meter. A millimeter is 1,000th of a meter. A micrometer is a millionth of a meter, and a nanometer is 1/100000th. And so all of these are going to be the common ones that we use, and they can be used for anything. So you could have a microsecond, you could have a centigram, you could have a nanokelvin. They can be used with any of the measurements, and this is just telling you how big or small it is from the base unit. If you would like additional help with prefix multipliers, please let me know. This will not be the last time that we see them. Volume is a derived unit. It is any length measurement cubed. So it tells us about the amount of space something occupies, and we're pretty familiar with volume. We deal with it on a regular basis. We can measure it in liquid volumes. We can measure in solid volumes. The SI unit that is used is a cubic meter, but this is a very large volume, not something that's practically measured in a lab. And so we frequently instead use a smaller unit, which is a cubic centimeter. It's a much more manageable volume. And you may have heard, so even in our daily lives, you may have heard somebody refer to giving somebody 3 cc's of a drug. That stands for cubic centimeter. So 3 cc's is 1 cubic, or is 3 cubic centimeters. But if you want to convert that, that means that it is 3 milliliters. So 1 cubic centimeter and 1 milliliter are the same volume. This is an important conversion to remember. It allows you to transfer between solids and liquid measurements easily.